Okay. All right. So, example. Let's say we have this massless pulley, and we have two masses, and one is 1 kilogram, and the other is 3 kilograms. Okay, and we want to know the acceleration, let's say of either one, but let's say what is acceleration of the masses and the string tension. Okay. Now, first of all, is it obvious to you that it will accelerate? Well, it's not balanced out, right? Obviously, there will be some acceleration. Now, is everybody clear that the heavier mass will be the one falling down, right? That makes sense. Okay. So this 3 kilogram mass will fall down, the 1 kilogram mass will go up. Now, I'm going to define what I call the S direction. And because we got used to thinking about gravity making things fall, where positive was in the up direction and gravity will go down, I will also make the same convention that my positive X direction will be opposing the falling motion, so it will be going like this. Just because that's how we thought about things falling, so we were used to that. And so this will be my positive S direction. Okay. Is everybody good with that? Okay. So on this side, the positive S direction is going up, and this side of the positive S direction is going down. All right. First thing we'll do to get the acceleration of the masses, we'll consider both masses together. Okay. Now let's figure out what are the forces on the masses. So I have the weight of a 3 kilogram mass. That's just mass times g, right? M times g. So that will be 3 kilograms times g, which is 9.8, 0 meters per second squared. I suppose I can. So we want 3 times 9.8, so that's 29.4. All right, and then we have this weight, so that's 1 times 9.8, so 1 kilogram times 9.8, and so that's 9.8 newtons. All right, is everybody good on that? Sorry, it's a little crowded here. Okay, so now what we're going to do is we're going to figure out the net force in the S direction. So I'm considering both masses together, so I'm not talking about the tension that's internal to the two-mass system. It's what connects my masses together. So I just want the external forces, things that are acting on my system. So I have F net in the S direction. Let's get rid of this bar here. Okay. I have the net force in the S direction. Okay, so I have this 29.4 newtons. Should I make that positive or negative? Okay, because it's going in the negative, this is the positive S direction, so I have 29.4 newtons. And then I have this 9.8. Should it be positive or negative? Yeah, positive, because on this side here, the positive S direction is the same way the weight is going. So positive 9.8 newtons. Okay, so that comes out to minus 19.6 newtons. Now we also know from Newton's second law that the net force in the s direction should be equal to the mass times the acceleration in the s direction. So what will the mass be that I use in this case? 4. Okay, everybody good? It's 4? Because I'm considering both together, so that's why it will be 4. 4 kilograms. And then times the acceleration in the s direction. So now I have this is equal to the net force in the s direction. This is equal to the net force in the s direction. So I have 4 kilograms. Oops. 4 kilograms times AS is equal to minus 19.6 newtons. And so AS is equal to negative 19.6 divided by 4, which is negative 4.9 meters per second squared. I can put another 0 here if I want. Okay, so the minus sign tells me that the 3 kilogram mass is accelerating downwards, which we kind of expected. Okay. And the magnitude of the acceleration is 4.9. Any questions about this? Very good. By the way, if you wanted to check, you could simply check that what the 1 kilogram mass would be doing, and the 1 kilogram mass would be accelerating upwards with 4.9 meters per second squared, but that should be obvious. Okay, to find the tension, now let's find the tension. It doesn't really matter which object we look at. So let's look at the 1 kilogram mass. Okay, we can do it with the 3 kilogram mass as well. So for the 1 kilogram mass, we have the tension going up. We have the force of gravity going down, and we already said that force of gravity is 9.80 newtons. And on this side, the positive s direction is going down. All right, now let's work out the net force in the s direction on this 1 kilogram mass. So we have positive s direction, I have 9.8 newtons. It's going the same direction as the positive s direction, so it's positive. And then I have t going in the other direction, so I have minus t. Okay. Is everybody following me on this? You got that? If you're confused, stop me, and then I'll try to explain where it is all comes from. Is anybody confused? Yeah. Okay, very good. Okay, so the thing I'm looking at here is, I said the positive s direction is this arrow. Okay? So if it's pointing in the direction of this arrow, it's positive. If it's pointing in the opposite direction, it's negative. Okay? That's like my positive y-axis. So the 9.8, the arrow is going down, so it's the same direction, so that's why it's positive. The t is pointing in the opposite direction to these arrows, so it's negative. Okay? Everybody with me on that? Yeah, it's important that you know there's pluses and minuses, or else everything gets messed up. Okay, then we also have Newton's second law. That the net force in the s direction is equal to the mass times as, the acceleration in the s direction. What mass should I use here? Yeah, just this guy, right? There's only this one we're looking at, 1 kilogram. So we have 1 kilogram times as. We solve for as as negative 4.9 meters per second squared. Okay, so I can finish up writing this. I get negative 4.9 newtons. All right, now I have two expressions for the net force in the s direction. I have 9.8 minus t, and I have 4.9 with a negative sign. So they must be equal to each other. 9.8 newtons minus t is equal to negative 4.9 newtons. Okay. Is everybody with me so far? One formula came from just writing down the forces, getting the net force. The other formula came from saying Newton's second law, the net force is equal to the mass times the acceleration. Put these two guys equal to each other, I get 9.8 minus t is equal to negative 4.9. Okay, everybody's on top of this? Good. Okay, so now we can solve for t. T is 4.9 plus 9.8, and that comes out to 14.7 newtons. Okay, any questions? Yeah.
So how did you know how to put together that last?
Okay, so the general pattern is we first draw first of all we get the direction of which things are positive and negative. So we have this positive direction. Then we draw the forces on the object. Okay? Either we do the object is both masses together and we put in the external forces, these two guys, or else we do one of the objects, like here. And then we say the net force is equal to the sum of the forces, with the positive sign for this and the negative sign for that. And then we say, we also know the net force is equal to the mass times acceleration from Newton's second law. Okay. So we have net force is mass times acceleration. We had already solved for the acceleration. And so that's why we knew this. And now we have two things. The only thing we don't know is t, and so we can get t. All right. Sure. Yeah. Okay. Yeah. So that's a great question. The way I am defining things is that t is the magnitude of the force, and the arrow is telling me which way it points. So if I got a negative for t, it means I had a very strange string that was actually pushing rather than pulling, and I would never get a negative t. Yeah. So if you get a negative t in a tension, you did something wrong. Yeah. Okay, yeah, that doesn't actually matter. All right, I'm trying to be consistent just because I like the problem to be. So when I try to make a convention, I try to make it so that as few students are confused as possible. If I went the other way, I think more students would be confused. So I chose it that way because I knew that the 3 kilogram mass was the one that would fall. And I was trying to make it look like a falling object where the positive y was going up. Okay? But it actually doesn't matter at all. It would work the same way. Okay? That's right. So if it was just like this, then it would be holding a 4 kilograms times g force. Yeah. Okay. Okay. So you're already looking at the answer here, what you're including. Yeah. So that's a good point. So notice that when the weights are steady like this, okay, that the tension, right? So it's a little bit complicated because there's no way to stabilize it with unequal masses. It will just always do that. Okay. But if I were to, for example, imagine this was 3 kilograms, this was 1 kilogram, and I tied the strings together, then the tension of this support would be the sum of the masses. Okay. But now what you're seeing is it's not equal to the sum of the masses because it's doing something kind of complicated to accelerate it. Okay. Yeah. To some extent, awesome. Okay, now I have to put my password. Let me just make sure this is still working. Yeah, okay. Yeah, the reason why it's actually not supporting so much is because the system is falling a bit. It's actually accelerating downwards. And whenever something's falling, it's not, you're not supporting it, you're letting it drop down. So it's not supporting quite as much. You could actually deduce that. There's a very simple relationship. But yeah, we don't usually talk about how much force the pulley is supporting, but it's just going to be twice the tension. this is great. So if you are stuck on something, there's a chance there's 2 or 3 other people with the same question, so don't be shy. And I actually enjoy answering the questions because it helps me. Oh, there's no. Yeah, so the first step is to figure out what is positive and negative. Set a convention for which way to go. Then focus on which object you're going to do Newton's second law on, whether both masses together or one mass. Okay. And then draw the three-body diagram to put all forces on. Then get the net force in a given direction. And then get the net, say the net force is equal to mass times acceleration, and then solve. All right, let's go on. By the way, I didn't actually tell you, there's a name. So if you suffer through the solution of this problem, I should tell you the name of it so it will be etched in your brain forever. This is what's called the Atwood machine, or a class of problems, Atwood's or Atwood machine, okay, named after somebody. I don't know the history. You can look up who exactly Atwood was. Okay. Let's go on. So now we're going to talk about some new stuff. We're going to combine uniform circular motion with Newton's second law. So we're going to combine, we're going to apply Newton's second law to uniform circular motion. Okay, so this is an application that really has something you probably think about every day, right? So this is a good example of physics that impacts your commute or your travel. If you drive, if you drive a car, you ride a bike, even if you run or use one of these scooters or whatever. Okay. Okay, so we have a circle. Remember, uniform circular motion, the deal is we have something going around a circle. The velocity is tangent to the circle. The speed remains the same, so constant speed. So speed is the magnitude of the velocity. And we have acceleration. There's this acceleration. Okay, and this acceleration is what's called the centripetal acceleration. There's no tangential in this case because it's constant speed. And the centripetal acceleration the formula is, and what is the formula? V squared over r. Okay. And the direction points towards the center of the circle. All right. So if I were asked to ask you what is the acceleration of this object going around a circle, it's very straightforward. It's this centripetal acceleration that points towards the center of the circle. So this object has an acceleration. Okay. Since there is a net acceleration, there is a net force by Newton's second law. And if we just talk about the magnitude of the net force, to be clear, I'm stripping away the direction, just taking the magnitude. That will be equal to the mass times the acceleration. And because the acceleration is just the centripetal acceleration, we get this formula mv squared over r. So there's no dot here. I just mv squared over r. Okay, so think of this as, this is the net force required for uniform circular motion. Right? The idea is that if we didn't have this force, without this force, the object would travel in a straight line. In fact, we had a question on that in the quiz. Maybe it was one of the last problems, right? What happens when the truck or whatever it was, car exits the highway, hits the icy patch, what happens? Which way does it go? Okay, so the object would travel in a straight line. Oops, I was supposed to say a lot. All right. So there's a name for this. This net force, this required net force is called the centripetal force. Now, I actually don't really like to call it that because sometimes students think of the centripetal force as some new force that they have to learn that we didn't have before. And that's completely incorrect. The centripetal force is not a new force. It's simply the required net force to keep the object going around in a circle. In other words, if I were to look at this, I would take one of these weights, take the string out, and spin it around my head. Okay? If I cut the string, the weight would go flying into the audience, you guys. Okay? But it's the string that, as the weight goes around the circle, it's the string tension that pulls the weight in that will allow it to keep going around in the circle. Okay? So the string tension is what, in that case, that would be the centripetal force. Does that make sense? Okay. So it's not a new force, it's just what you need to make it go in a circle. So as I said, here's an example. If I have, let's say, a ball, a string, let's say the ball is on some frictionless surface, so you don't have to worry about gravity at this moment. And then so I have, let's say, this is the velocity, the speed of the ball going around the circle. Then we have this tension of the string. It's pulling inwards. And the tension of the string. So this is some ball. This is a string. It's going around a circle. Okay. And the radius is, so that means the tension is equal to the net force, which will be equal to mv squared over r, where r is the radius of the circle. Okay. Are there any questions about this? Okay, let's take another example. Let's talk about a curved flat road. Suppose we have curved flat road. Okay, let's say we have this road here. It's flat, and let's say there's some sort of, let's say you're in a little car. Let's just sketch a little car here. You're going along here. Okay, and you're going with some speed around the curve, and here's the center of the circle, and here is, oops, what's going on with my, why is that doing that? I don't know. It's probably because it's on battery versus being plugged in. That might be the difference. Oops. I didn't want to do that. I wanted to do this a bit. Everything's fine. As far as it's still going. Yeah. Thanks for asking. Okay. And so we have, there needs to be some force that is providing the centrifugal force. As I said, to go around a circle, you need a centrifugal force, a net force. Does anybody know what provides that force? Yeah, that's friction. Friction is providing that force. Okay? And it's actually the force of static friction. You might be confused by that because I told you that static friction is when things are not moving, but kinetic friction is when it is moving. Well, if you're not skidding, if your tires are rolling perfectly and not skidding and sliding on ice or something, then your tires are actually, what is happening is you're what's a good example? I need something circular. Okay, so when something's rolling without slipping, what's happening is that the bottom surface as it rolls without slipping, there's actually no slipping. Does everybody understand? It's not sliding like this. It's actually contacting and there's no slipping. In that case, it really is static friction. Okay? And the static friction is actually not forward and backwards. It's actually side to side. It's actually, what's happening as you turn, let's say I'm going to go around the curve like this. Okay? I turn my steering wheel like this, and my tires are not forward but slightly turned like this. It's actually the side-to-side static friction that pushes off, that makes me, instead of going straight, slant a little bit this way. And every time I'm slanting a little bit this way, that's why I keep changing my direction. Okay? Everybody you got that? So it's static friction that's providing this force. So the static friction is providing the net force, the required net force. So if I were to consider a little car, let's draw it head on. Let's put it in a little, dress it up. Okay. And we have normal force going up. We have the force of gravity going down. They cancel each other out. It's on the ground here. And then way over here is the center of the circle. Okay, this is the center of the circle. Okay, and now this force of static friction is going to be providing the centripetal force. In this head-on view, it's pointing towards the center of the circle like that. And that will be the net force, because the normal force and the force of gravity will cancel out. And so this will be F net, which is equal to mv squared over r. Okay. Any questions about this? Okay. Now let's do a quicker question. Okay. All right, the question is, a roller coaster makes a vertical circle of radius 20 meters. And the question is, what is the minimum speed required so that people basically don't die? Okay, people don't fall at the top of the circle. So you see, this is actually relevant. Right? If you're designing an amusement park, you don't know this physics, you're kind of taking a chance here. Okay? Don't fall at the top of the circle when upside down. Okay? So here is so if you're not clear what's going on here, you do a little circle. Okay, it's not really a circle, it's a loop thing, but I'm not drawing that. And we have a little person in the vehicle enjoying the roller coaster ride. The arms up now. And it's going, oops, sorry, that was supposed to be straight. Hit a little bump in the desk there. That's going with the speed v, and the radius r is equal to 20 meters. And we want to know what's the minimum speed needed. So let me give you some choices. Okay, 5 meters per second, 8 meters per second, 12 meters per second, 14 meters per second, 16 meters per second. Okay? So I will, where did my, okay, somehow I can't find my, my clicker thing, what happened to it. Once I find my clicker thing, just 1 second, let me find my clicker thing. Oh, okay. It disconnected when it went into screensaver mode. So just 1 second, it will be operational. Okay, it's on now. I have to. Okay, so let's extend this. So the radius is 20 meters. All the information is right there. So, yeah, so I've got a question about what do we do with normal force gravity, right? So the question is, what is the minimum speed required, right? So think about if I made it a little bit less than the minimum, then the person will start to fall, right? If this person is starting to lose contact with the seat, then there is no normal force. That's the minimum. Right? So the minimum is when normal force is 0. So it's a little hard maybe to think about it, but let's view the person upside down. Okay? The person is sitting on the thing but upside down. There's a normal force going in this direction, same as gravity. If the person is starting to fall, the normal force is going to be 0. So that's what we're talking about here. Okay. All right. So go ahead and make your choice, and then we'll go over it, and they'll be all. Everybody made a choice? Okay, I'm going to stop. If you haven't made a choice, go ahead and do it now. And let's see what people have said. Okay, a lot of people say D. Let's take a look. Okay, so as I said, the normal force is going to be 0 when we're at the minimum speed. So in general, you have this the person is being pushed. This is the person, okay, in the thing, being pushed by the normal force of the seat and the force of gravity. But we are making the speed at the minimum, so there's no normal force. So only gravity is providing the centripetal, the net force. So we need the net force, so the centripetal force needs to be v squared over r. But we also say that the only force will be the force of gravity, which is m times g. Okay? Everybody's with me on that? Okay. Now, so mv squared over r is equal to m times g. M's canceled, which is great because we had no idea what m is. Okay? So now we have v squared is equal to gr. And so now we have v is equal to square root of gr. Plug in the numbers. We have 9.8 times 20. And we get 14 meters per second. Okay, now before I let you go, let me just ask one question about this. Suppose you go faster than 14 meters per second. Is it clear what's going on in that case? If you go faster, then what will happen is that the required centripetal force needs to be bigger, right? Because you're going faster. And what provides that extra oomph of the centripetal force in that case? Any ideas? It's not gravity. Gravity is not going to change. Let's suppose we go at 30 meters per second. Yeah. It would be the force. It will be this normal force. In that case, the seat will be pushing the person down. Person down. Okay. Okay. I'll see. Oh, sure. See you guys tomorrow. All right. On Monday.